Can you hear me? Awesome. So I want to talk a bit about ZVOL performance. More specifically, a patch I got merged over the summer that could increase or decrease your ZVOL performance. So back in August of 2021, our archive team at Lawrence Livermore National Laboratory was testing out some new hardware. And they were benchmarking ZVOLs on ZFS. And what they were seeing was when they would do parallel DD writes, just normal DD writes, they would get about 1.7 gigs a second. And then when they reran the same test with ODirect, they would get 2.9 gigabytes a second, so basically line rate. And they were saying, well, why is that? And for those of you who don't know, ODirect is a flag that you can pass to open and open at. And it's a hint to the kernel to say, don't cache anything I'm writing, just send it directly to the device. So I reran the test setup that they were using in the archive team, and I hit the same results. So I started down the rabbit hole. So this is a non-ODirect write. This is just a normal write. And flame graph that I learned about at a past OpenZFS conference, I think from one of your presentations, Matt. So here with the non-ODirect write, you can see ZVOL write is like 60% of the total time. And if you look at the ODirect, it's maybe 20%. So if you drill down and you go into ZVOL write, in the non-ODirect case, you can see that almost all its time is taken up by dbuf find. It's actually 18.5% of the total CPU time is in dbuf find for non-ODirect writes. But with ODirect, it's 1% of the time. So something's going on in dbuf find that's eating up all of our performance. So before I go into that, I want to give a little bit of background. The ZVOL driver is a block device driver for the Linux kernel. And the API it historically used was through submit-bio. Submit-bio is a function that you pass in and you say, whenever you have an IO that you want to write to my block device, pass this struct bio. And what I was seeing was when you would do ODirect, you'd get these nice big, like, half megabyte or megabyte block IOs. But if you did regular writes, so non-ODirect, you get these tiny little 4K BIOs coming in, just tons of them. And that makes sense because when you're doing a regular write, the kernel's going to block or cache everything in the page cache. That's why you're getting all these little 4K block IOs. So how does that relate to dbuf find? So dbuf find is a function that looks up the dbuf for the block that you're writing. The dbuf is like the internal representation of the block in cache. And so you have to lock the block before you write it. And so as you can imagine, there are tons and tons of blocks in cache. So when you want to write, you have to find the block and lock it. Well, you can't just iterate through all the dbufs because that's inefficient. So we store the dbufs in hash arrays. So basically, each block will hash to a bucket. So dbuf find, once it finds the block, it'll lock it and return. That's what the function does. OK, this is a simplified view of what's going on. So let's say I want to write block 0. I first need to hash the bucket, in this case bucket 3, and lock it so that nobody changes out the list from under me. And then I iterate through all the blocks in the bucket until I find 0, and I lock it. OK, well, you can probably see the problem here. If you do a 1 megabyte write and it's broken up into little 4K block IOs, then you're going to have 256 little block IOs all trying to lock the same block. And the way it works in the ZVOL driver is that when a block IO comes in, it'll hand it off to a thread. So let's just say you have 16 CPUs, 16 threads. So it hands off all these little block IOs to all these threads, and they're all trying to get the same lock. So that's why you have this massive lock contention in dbuf find. But it's actually worse than that, because this is a very simplified view. There is not one lock per bucket. There's actually one lock per group of buckets. So when you load up the ZFS module, it'll create the number of buckets based upon how much available memory you have. So it could be, thousands. But historically, we always hard-coded 8,000 locks. So one lock would handle multiple buckets. So when you had all this lock contention going on, you could be holding a lock that other parts of the block device, you wouldn't be able to access it there either. Luckily, a recent change that Brian Bellendorf checked in makes it dynamic, so that there's just one lock per 128 buckets. So what's the solution? Well, I mentioned that the historical interface between the kernel and the block driver was the submit BIO interface, where you'd get one block IO at a time. But there's a semi-recent interface that they added called blk-mq. It was added, I want to say around the 3.10 or 3.15 kernel, but the one that we support, because they made some changes, is like the 4.13-ish kernel. So anyway, it's a new API for talking to your block driver. And the difference is, instead of getting tiny little block IOs from the page cache, you get one big struct request that points to multiple block IOs. So that way, you can lock the block per big request rather than per little block IO. So that's the main benefit to ZFS, but there are other benefits too. So the reason it's called blk-mq is that it's a queued interface. So instead of with submit BIO where you submit and then you wait, okay, next one submit, it just puts it into a queue with blk-mq. So the kernel can rearrange or merge IOs if it wants within the queue. And then when it's ready to kick it out of the queue, then it wakes up your driver. And it's called multi-queue because there's not just one big queue. There's multiple queues that you can spread across multiple CPUs. So you get better parallelism. All right, so on to the benchmarks. So here I took 8 NVMe drives, made them into a RAID 0 pool, and then just ran DD. And this is 1 DD to 1 ZVOL running regular non-ODirect. And so you can see with the old submit BIO interface, I got between 400 and 600 megabytes a second at different block sizes. And then with blk-mq, I got around 750 to 900-ish. So pretty good speed up there. This is the same benchmark, 1 DD to 1 ZVOL, but with ODirect. And you could see it's close to the same, but blk-mq is actually a little bit worse in all the cases. And I'll go over later why I think that is. OK, this is a parallel write benchmark. This is spawning off 16 DDs in parallel writing to 16 ZVOLs. And this is kind of the best case scenario for blk-mq. You go from anywhere from a 2x speedup to a 4x speedup, depending on your block size. But then if you run that same benchmark with ODirect, they're basically the same. OK, now let's look at reads. So this is a single DD read from a single ZVOL non-ODirect. And the performance is close to the same, but blk-mq is a little bit better at 8K vol block sizes and 1 meg vol block sizes. And then parallel read, they basically perform the same. Again, parallel read, 16 DD reads, non-ODirect. Now single read with ODirect, they basically perform the same. blk-mq is a little bit faster with 1 megabyte blocks. And then parallel read with ODirect, they basically perform the same. I think some of the differences you see here is just test noise. OK, so now I want to look at all those same benchmarks, but look at the CPU usage. And here I was just running the time command. So I was looking at wall clock, real time, and system time. So CPU time and wall clock time. So real is the wall clock time, sys is the CPU time. And like before, you can see the yellow line is the old submit BIO interface with, this is a single write. So it takes a lot longer to complete, and block multiqueue is a lot quicker. But you can also see the red line is the block multiqueue system time. And you can see that the block multiqueue system time is higher than the submit BIO system time. So it's using your cores more efficiently. And then this gets even more pronounced in the parallel write case. Again, we know block multiqueue is a lot faster here, but if you look at the red line, which is the block multiqueue CPU time or system time, and then you compare that to the submit BIO system time, the green line, you can see that block multiqueue is really using more of your cores, which is good. I mean, you paid for those cores, you want to use them to get faster writes. Single writes with ODirect, you can see that block multiqueue takes longer, which we knew, and the system time is about the same. With parallel writes, block multiqueue, wall clock time was about the same, but it took more system time, so that's not as good. Looking at single reads, non-ODirect, block multiqueue was a little bit faster at 8K, which we knew, and about the same amount of system time. And rounding it out, parallel reads, non-ODirect, basically the same. Single reads with ODirect, basically the same. Parallel reads with ODirect, block multiqueue is a little bit slower for the 8K block size. Okay, so those were all sequential. This is some numbers that Tony Nguyen ran. My point, these are a bunch of different tests that he ran. I don't want to get into the actual numbers because it's all over the board, and that's kind of the point. The point I want you to take away from this is that block multiqueue is not an instant win. You really have to try it with your workload. It may be a lot worse for random reads and writes. If you're running ODirect, you probably don't even want to use it. So in summary, block multiqueue helps when in the non-ODirect cases, especially with non-ODirect writes, especially parallel sequential writes. It can help a little bit on sequential reads, but otherwise, if you're using ODirect, you really don't need block multiqueue. Now, I mentioned that block multiqueue was a little bit slower in some of the cases, and I said I wanted to touch on it later. And this is the reason why I think it's a little bit slower. Check my time here. When you do a write with block multiqueue, it gets put into a queue into the kernel. And then at a certain time, the kernel is going to kick it out of the queue to your block drivers, the ZVOL driver, to say process it. So that takes time. Once it goes into the ZVOL driver, then we spawn off a thread to deal with it. That takes time. So it kind of gets double queued, 2 wake-ups. And it doesn't necessarily have to be that way. You could do a write, it goes into one of the block multiqueue queues, and then when the kernel wakes up your block driver, we could just synchronously do a write. We could just synchronously call ZVOL write. And when I tried that, it worked for like the first 4-ish writes, and then it would kernel panic. So basically, the whole reason why it's doing this double queuing is to get around a kernel panic. But if we could figure out why it's doing that, I think it would lower the latency, and we would get better performance. So these are some of the tunables for block multiqueue. These are kernel parameters. So block multiqueue is not enabled by default. It's disabled. So you have to go in and set ZVOL use block multiqueue to 1 to use it. And this setting takes effect at ZVOL load time. So for example, if you want to use block multiqueue, if you want to test it out, you would set this to 1 and then import your pool, because that would load your ZVOLs. Or you could create a ZVOL after it. Or you could even have cases where you create a ZVOL, set this value to 1, create another ZVOL, and those 2 ZVOLs use the 2 different code paths. One uses submit BIO, one uses block multiqueue. ZVOL threads, this is actually an existing pre-block multiqueue parameter. This is just the number of ZVOL processing threads in the ZVOL driver. I think it's default set to 1, which says use the number of CPUs. ZVOL block multi-queue threads. You can think of this as the number of queues to tell the kernel to create. I think this is also set to 0 to say, okay, default to the number of CPUs. ZVOL block multi-queue queue depth. You can tell the kernel how big you want your queues to be, but in all my testing, it didn't really affect performance at all. And then finally, ZVOL block multi-queue blocks per thread. This is kind of a way of telling the kernel how big you want your IOs to be, or what is the optimal size I would like my IOs to be. And this is an interesting value, which I'll get into a little bit. So I mentioned because of the locking, you want to process big block IOs. Or more specifically, you want to process block IOs that are the same IO size as your vol block size. So you'd say, okay, well, if my vol block size is 1 megabyte, then I want to tell the kernel, I want 1 megabyte block IOs. And you can do that, that's fine. But then remember that it's doing all this overhead with this double queuing. So wouldn't it make sense to try to process like 2 megabytes or 4 megabytes or 8 megabytes so that you can process more data for those 2 wake-ups? And this is where I kind of went down the rabbit hole. So the kernel provides this function called block-queue IO opt, which is documented as set optimal request size for the queue. But if you set it to 1 megabyte or whatever you want to set it to, it doesn't seem to give you those IOs. So I didn't have any luck with this. But there's kind of a roundabout way to do it with these 2 other functions. So there's block-queue max segment size, which you can think of as like, what block IO size do I want? And then block-queue max segments, which is how many block IOs do I want per request? And by setting these to, in a certain way, to fit your block size, you kind of get what you want. So then the question becomes, well, what's the optimal block size? Is it 1? If I have vol block size as 1 megabyte, do I want it to be 1 megabyte or 2 megabytes or 4 megabytes? So I ran some benchmarks to try to find the sweet spot. So this is a graph with different numbers of blocks, or different request sizes, and different numbers of threads. But the takeaway here is the more blocks you request, the faster your reads go. So this is a parallel read test. So more blocks, better for reads. For writes, you see the same thing. These are non-O-direct writes. You get a lot more performance with requesting 16 blocks versus 1 block. Consequently, you get better performance with fewer ZVOL threads. So that might also be something you want to tune when you're doing benchmarking. Now here's where it gets interesting. Before it looked like, well, more blocks better, right? And here you can see with writes, more blocks is better. But this is looking at O-direct reads and writes. And with O-direct reads, you actually get better performance with fewer blocks, with 4 blocks. So this is yet another tunable that you'll want to benchmark on your workload to try to get the best performance. I think I set it to default to 8 blocks in the driver currently. Just a few other interesting commits. I want to talk about reduce debuf find lock contention. This was something that Brian merged. And this basically converts all those debuf locks from a mutex to a read-write semaphore. And this could potentially help if you have like mixed reads and writes. Although we did get a report from one of our vendors saying, we didn't get as good of performance with this. And then the other commit I want to mention is this dynamically sized debuf hash mutex array. I did talk about this earlier. This is the commit that makes the number of locks dynamic. So you go from the 8,000 hard-coded locks to 1 lock per 128 buckets. Okay, so what else can we do beyond block multi-queue? What are some future things we could do to improve? Well, I've already talked about the double queuing. I think that's probably the biggest win with the least amount of effort. if we can just synchronously call ZVOL write from whenever we get a block I/O, I think that's going to be a lot better. The second thing I mentioned is support vanilla request queues. So I kind of lied. There's the old submit BIO interface, and then there's the new block multi-queue interface. But there's actually an interface in between that's just vanilla request queues, just normal request queues. And so we could support this with not a whole lot of effort. And that could be useful if you're running a kernel that's kind of in between submit BIO and block multi-queue. Like maybe if you're running rel 7 and you really want ZVOL performance, you could potentially implement request queues in the ZVOL driver. The direct I/O patch, this is a patch that's been going through review that Brian Atkinson is working on to implement true direct I/O in ZFS. And this is something that gave us a huge, huge performance improvement with data sets. I haven't tested it with ZVOLs, but we got like a 60% write speed up using direct I/O. So if you want, I would recommend everyone try to get this patch reviewed and merged. And then the last thing I wanted to mention was kind of a crazy idea. So I mentioned that you kind of get the best performance with ODirect. It's kind of a magic button that gives you better write performance. But you have to specify ODirect when you call open or openat. So it has to be done at the application level. So you either have two choices. You have to recompile all your applications to pass in the ODirect flag at open, which no one's going to do. Or you could do this thing called library call interception, where you can hijack calls to, say, open or openat, redirect them to your library, and then in your library, you add in the ODirect flag and then just call the normal ODirect. The idea there is you could say LD library path equals lib fake odirect.so, and then you run with your binary name after that. And then your binary would always use ODirect with writes. So this is what I want to do for the hackathon tomorrow. And we'll see if this helps. So this would only help if you're using it with an application that's using ZVOLs. But it could also help if you have a file system on top of a ZVOL. You could use this hack too. So this could speed up like copy, rsync, tar, things like that. So we'll see how that goes. And then I just listed the pull requests that I had. This got merged in June, I think. Block multi-queue is only in master. We haven't pushed it out to any of the point releases. And again, you have to manually enable it. So that's what I've got. Any questions?
Basically, are there situations where your big requests, the many little requests that are part of your big requests, you split across multiple stuff?
No, I don't think it would work that way. I think it would, when you do a write, it would put it into one big request, possibly merging it with another request in the same queue. So I'm not sure why fewer ZVOL threads in that case made it better. Maybe it opened up more threads for the actual underlying block device. I don't know. Yes. So the question is, have I considered the async DMU pull request as an improvement? I haven't looked at the async DMU pull request, but I'll take a look. Yes. Yeah, the question was, did I try setting ZVOL request sync? Did I try setting that to 1 to get around the double queuing? Yes and no. That code path that you're talking about is what I used for the synchronous write. I didn't set that value. I just hard coded it and tried it, and that's what was giving me the problem. Any other questions? All right. Thanks.
We have a break until. Right on. Thank you. Good job.